Right now, at the center of our galaxy, 4 million times the mass of our sun is compressed into a region smaller than our solar system. It has been warping space and time for billions of years. We just took its picture. Black holes are the universe's most extreme objects, regions where gravity has grown so intense that nothing, not even light, can escape. They range from stellar remnants just a few times the mass of our sun to supermassive giants billions of times more massive, anchoring the hearts of nearly every large galaxy. For decades, we could only sense their presence through the motions of stars and gas swirling around them. Then, in 2019, humanity achieved something once thought impossible. We photographed one. This is how we finally captured the uncapturable. When a massive star, one at least 20 times heavier than our sun, exhausts its nuclear fuel, the consequences are catastrophic. In less than a second, the iron core collapses under its own gravity. The outer layers are blasted away in a supernova explosion bright enough to outshine an entire galaxy. But if the remaining core exceeds about 2 to 3 solar masses, not even the pressure of densely packed neutrons can halt the collapse. The core keeps compressing, past neutron star density, past any known physics, into a singularity, a point where our equations break down entirely. A stellar black hole is born. Surrounding every black hole is the event horizon, the boundary beyond which escape becomes mathematically impossible. It is not a physical surface, no wall, no barrier, just a threshold. Cross it, and every path through space-time, even the one pointing outward at the speed of light, curves back inward. The Schwarzschild radius defines this boundary. For one solar mass, it is about 3 kilometers. For Earth's entire mass, it would be barely 9 millimeters, smaller than a marble. The singularity itself is not at the center of a sphere of space, but at the end of everyone's future. At the heart of the Milky Way, roughly 26,000 light-years from Earth, lurks a supermassive black hole called Sagittarius A star. Its mass is 4 million times that of our Sun. Its event horizon spans roughly 24 million kilometers, yet that fits comfortably inside Mercury's orbit. Despite its enormous gravity, Sagittarius A star is unusually quiet. Most supermassive black holes devour surrounding gas and blaze as brilliant quasars visible across the universe. Ours is a sleeping giant. Astronomers believe it last feasted on a significant gas cloud roughly 2 million years ago, a meal that briefly made our galaxy's core blaze, with X-rays visible from the Magellanic Clouds. For 50 years, astronomers suspected something massive and dark lurked at the galactic center. The proof came from watching stars orbit nothing visible. Two independent teams, one led by Reinhard Genzel in Germany, another by Andrea Ghez in California, spent decades tracking the precise motions of stars deep in the galactic core. One star, designated S2, became their smoking gun. It completes a full orbit every 16 years, swinging within 120 astronomical units of the center at up to 3% the speed of light. Only an invisible mass of 4 million solar masses could produce that motion. Genzel and Ghez shared the 2020 Nobel Prize in Physics for this proof. Imaging Sagittarius A star posed an extraordinary challenge. Its apparent size in our sky is roughly 50 micro-arcseconds, equivalent to photographing a golf ball sitting on the surface of the moon. No single telescope on Earth can achieve that resolution, so astronomers built a virtual one. The Event Horizon Telescope links 8 radio observatories scattered across the planet, from the summit of Mauna Kea in Hawaii to the South Pole Telescope in Antarctica. Using a technique called very long baseline interferometry, they combine signals to form a dish effectively the diameter of Earth, powerful enough to detect a donut at lunar distance. On April 10th, 2019, the world saw a black hole for the first time. The image showed M87 star, a black hole 6.5 billion times the mass of our Sun, 55 million light-years away. As a glowing asymmetric ring of superheated gas encircling a dark central shadow. The brighter southern arc is caused by relativistic beaming. Gas moving toward us at near-light speed appears far brighter. 3 years later, on May 12, 2022, the EHT team released the first image of Sagittarius A star itself, our own black hole, photographed. Both images confirmed a prediction made by general relativity more than a century earlier. Black holes span an astonishing range of scales. Stellar black holes, born from collapsing stars, run from about 3 to roughly 100 solar masses. Intermediate black holes, thousands to hundreds of thousands of solar masses, have been detected growing in dense star clusters. At the top sit the supermassive behemoths. Sagittarius A star, at 4 million solar masses, is modest by these standards. M87 star is 6.5 billion solar masses, and at the extreme end sits Ton 618, a quasar hosting a black hole of 66 billion solar masses. Its event horizon is wider than our entire solar system. Black holes guard some of physics' most stubborn mysteries. Stephen Hawking showed that quantum effects near the event horizon should cause black holes to slowly radiate away energy and eventually evaporate. But what happens to all the information about everything that fell in? This information paradox remains unsolved. It sits at the collision point of quantum mechanics and general relativity, and resolving it may require an entirely new theory of physics. The Next Generation Event Horizon Telescope, with more observatories and higher frequencies, aims to shoot movies of gas swirling into Sagittarius A star in real time, bringing us ever closer to the edge of the unknowable.